So this is an example of what we call linear trig equation because there's just one trig function and it's not squared or anything like that. So all we're going to do is we're going to try to isolate cos theta. So we're going to solve it like we would a normal equation. We'll subtract over the radical 2. Leaves me with 2 cos theta equals negative rad 2. And then I would divide by 2. So now I have that cos theta is negative rad 2 over 2. So then remember, like we do a lot in this unit, we're now trying to figure out the angle for which cosine is equal to that. So if you know your chart, this should be familiar to you that this gives us a reference angle of 45 degrees. But that's not one of our answers because it's negative, so then I have to go to my ASTC and think about where is cosine negative. And that would be in quadrants 2, so I need something here with a reference angle 45 and in quadrant 3, so here. So that would give me 135 would be the angle in quadrant 2 because I subtract 45 from 180, and then 225 would be the angle in quadrant 3 because I would add 45 to 180. So those are my two answers. So then we have some more complicated equations. Once you introduce something squared, then this looks more like a quadratic equation. However, we don't want to have two different trig functions the way that we do. Our goal is to have just one so that we can apply some kind of factoring strategy, whether it's MAM, GCF, dot, something like that. So in this case, because I need just one trig function, I need to use a Pythagorean identity, and I can only plug a Pythagorean identity in for the function that's squared. So here, I'm going to actually use the identity cos squared x plus sine squared x equals 1. So that's the Pythagorean identity that involves the function we're dealing with, cosine squared. So before I can substitute it in, however, I have to isolate the cos squared, because right now I don't know what just cos squared is equal to. So I'd actually have to manipulate this one. If I subtract sine squared x on both sides, I get that cos squared x is equal to 1 minus sine squared x. So now, because I have an identity that's exactly equal to cos squared x, I can take this piece and plug it in to the cos squared. So I'm going to have a new equation. So I leave everything else the same. I leave that original 2. Now in parentheses, I'm inserting my identity. And everything else stays the same. Okay, now this is really good news because I've got sine everywhere. So now I can do what we call a let statement, and I'm going to then have my equation just be in terms of x's. So I go ahead and I let x equal sine x, and then I write this out the way that it would look now. So this would really be 1 minus x squared plus 3x minus 3. So anywhere there was a sine x, we took it out and left just an x in its place. So this one had to be squared, and the other one is just a regular x. Okay. Now I have to manipulate this and then ultimately solve it. Okay, so I came onto another page just because I knew I wasn't going to have enough space. So now I have to get this to look like something that I would be used to factoring. So I'm going to go ahead and distribute, collect like terms, and get this to look like a trinomial. So this would give me 2 minus 2x squared plus 3x minus 3 equals 0. So the first thing I can do is combine my like terms. So I've got 2 and minus 3. So this is negative 2x squared plus 3x minus 1. And now I also don't want to have my x squared term negative, so I'm actually going to divide everybody by negative 1. So now I have positive 2x squared minus 3x plus 1. Okay, so finally this looks like a normal MAM problem. So I'm going to go ahead, put my MAM on top. I need to multiply, in this case, to positive 2, and I need to add to negative 3. Okay, so if I kind of play around with the numbers, I should see that the two numbers that would work would be negative 2 and negative 1. When multiplied, they give me positive 2, and when added, they give me negative 3. So because I have a lead coefficient that's not 1, I do have to do those two fractions. So I'm going to do 2x over negative 2 and 2x over negative 1. Okay, this first one can be simplified, so this goes down to 1x over negative 1, and the other one stays the same. So now I write these out. X minus 1 and 2x minus 1 equals 0. So I've got it factored, and now all I have to do is drop and split. So when I do that, I get that x is 1 and x is positive a half. Okay, I've solved it, but I have to go back and remember that we had done a let statement. X is really not just x, it's sine x. So now I plug the sine x back in, and I have to figure out again at what angles will these values be true. So if I think about my unit circle, I've got those 4 important points. So this is my 1, 0. It's kind of hard to see, sorry. This is my 0, 1, my negative 1, 0, and my 0, negative 1. So those are helpful for me to have memorized, or at least to be able to visualize, because now it's easy for me to go look at it and say, oh, I can see where sine is 1. Sine corresponds to the y value, so that means this one is true when x is 90 degrees, because that's where my y value is 1. For sine x equals 1/2, again, I would need to know my chart, which I think we do by now. This would give me a reference angle of 30, because that's when sine is 1/2. And since it's positive, 30 is actually one of my answers. And then I would need to think about, okay, where else is sine positive? If I add a little ASTC up here, I see that it's quadrant 2. So I need someone in quadrant 2 with a 30-degree reference angle, and that would be 150. So that's my second answer that corresponds to 1/2. So I have 3 angles that satisfy this equation. And I'm done.